Hello and welcome to today's lecture on adiabatic logic circuits. This is a new class of circuits, obviously much different from static CMOS circuits, and we shall see how you can reduce the power dissipation in adiabatic circuits. So, obviously the circuit should be CMOS in nature, but adiabatic CMOS. And here is the agenda of today's lecture. After giving a brief introduction, I shall discuss the basic differences between conventional and adiabatic charging. Then we shall see how we can do adiabatic amplification, and then we shall discuss about realization of adiabatic logic circuits, and after that we shall have brief discussion on pulsed power supply, which will be required in implementing adiabatic logic circuits. Then we shall discuss partially adiabatic circuits to reduce the cost of implementation of fully adiabatic circuit. Then we shall conclude the lecture with some comments. So far we have seen that full swing voltage mode CMOS logic styles have been extremely successful both technically and in terms of market share. That means, the whatever we have discussed so far, they are known as you know, static CMOS circuits. Static CMOS circuits. And in static CMOS circuits, we have seen that there is a voltage swing between VDD and ground. So, there is a rail to rail voltage swing, and as we know, the basic implementation which is being done with the help of one PMOS and one NMOS logic block. So, we have got this is the PMOS and this is the NMOS, and output is taken from here, input is given here. So, here the output swings between VDD and ground, and we have seen that this is very a successful technology with lot of CAD tools available, and most of the VLSI circuits are nowadays realized by using this technology. But switching power dissipation of CMOS circuit with capacitive load has a lower limit of CL VD square by 2. We have seen that whenever there is a switching, I mean maybe from 0 to 1 or from 0 to 2, there is a transfer of energy, I mean there is a dissipation of power dissipation of CL VDD square by 2. This power dissipation always take place in each in switching, and total energy transfer from the battery or power source may be CL VDD square, but half of that energy is dissipated when it charges, when the capacitor charges, and remaining half is dissipated when the output goes from high to low. That we have already discussed that. That means, and that is the reason why in conventional circuit, to reduce power dissipation, we tried to reduce the supply voltage known as supply voltage scaling, or we tried to reduce the capacitance. Which capacitance? As long as the CL is fixed, VDD is fixed, this is the lower limit of energy loss part switching. This cannot be changed. So, you can say this is the lower limit. The power dissipation, switching power, that dissipation cannot be lowered than this one by using this conventional static CMOS circuits. Now, is there any way we can do it? Yes, the other alternative is adiabatic switching circuits, where the switching power dissipation is below this lower limit. That means, we shall be doing the switching in such a way that the energy dissipation, that means energy loss per transition will be lower than this. That means, and that can be done by using a technique known as adiabatic technique. This term adiabatic has been taken from thermodynamic processes. As you know, adiabatic systems do not release energy to the environment, or do not take energy from the environment. These are the typical characteristic of adiabatic systems. That means, no energy is transferred from the system to the environment. So, here also that is the basic objective, but how far that goal is successful, that we shall see, but this term has been taken, adiabatic term has been taken from this thermodynamic process that exchange no heat with the environment. So, in this in thermodynamic systems, essentially heat is the energy, and in fact, in our logic circuits also ultimately the energy is transferred to the environment in the form of heat. Now, reduction of power dissipation occurs at the cost of slower speed of operation. Later on we shall see in adiabatic systems the reduction in power dissipation will be taking place at the cost of speed. That means, we shall be trading power at the cost of slower speed, or in other words adiabatic circuits will be slower, and why, that we shall understand very soon. Moreover, it also allows the recycling of energy to reduce the total energy drawn from the power source, and another approach which is being followed in adiabatic circuit is to recycle the energy. That means, whatever energy has been transferred from the power source to the circuit will be transferred back after some computation is done back to the power source. So, that is the reason why these are also known as reversible logic circuits. That means, you are transferring energy from the power source to the circuit, and again you are recovering that energy by transferring back from the circuit to the power source. How can it be done, that we shall discuss little later. And you are familiar with the switching power dissipation in static CMOS circuit. We know that charging and discharging take place, leading to this switching power dissipation. Now, let us focus on the charging process of a capacitor. We have a capacitor. This capacitor is typically the load capacitance, or it can be any capacitance. This capacitance has to be charged. Simplest circuit by which you can do it is that suppose this is your power source VDD, and you can put a switch, and then you can put a resistor, and as you close the switch, at t is equal to 0, then what will happen, this capacitor, if there is no charge initially at t is equal to 0, the charge in this capacitor is 0, then it will start charging. And as you know, in case of whenever you are charging through a resistor, this is your R and this is your C or CL, whatever it may be. We know that initially the current will be maximum, because the voltage across the capacitor is 0. So, the entire voltage will be developed across this resistor. So, if this is the voltage VDD, then a current of VDD by R will flow initially. Then of course, this current will keep on decreasing with time, and it will become eventually 0, asymptotically it will approach 0, and the corresponding equation of current is I is equal to, as you know, is equal to e to the power minus t by R c. That means, it depends on the time constant and the rate at which it will discharge. So, this is the typical current drop, current that flows in this circuit. Now, if we consider the voltage that is developed across the capacitor, the voltage rises in the opposite way. That means, initially this voltage across this capacitor is say V o, let us assume the voltage here is V o. Initially it is 0 at t is equal to 0, and then V o will be equal to Q by C into 1 minus e to the power minus t by R c. That means, the voltage will gradually rise and eventually it will become equal to that VDD, it will become equal to VDD. So, we find that what is happening in this case VDD, this is the voltage across it, which will be equal to IR, that means, this has to be multiplied with R. So, it will be equal to IR plus Q by C, it will be V 0 is equal to V 0 into, sorry, it will be VDD by I believe VDD by C, V 0 will be equal to VDD by charge is equal to okay, charge, actually I have written it wrongly, charge Q by C, that means V is equal to Q into C. So, that means V is equal to Q into C. So, it will be actually expression for Q, charge that is built up is equal to VDD by C into 1 minus T by R C. So, it will be this plus VDD by Q by C, something wrong, Q is equal to VDD by Q is equal to, sorry I have made it, Q is equal to C into VDD. So, in this particular case this will be changing. So, it will be equal to it will be a changing, and that will be equal to VDD by into 1 minus e to the power minus T by R C. So, that means this VDD is not a constant in this case, you can say it is T Vt. So, it will be VDD into 1 minus T by R C. So, this will become equal to I into R plus Q by C, that means VDD will be equal to IR into Q by C. So, we find that with as the time progresses, this IR is this voltage will gradually come down, because current will gradually reduce. On the other hand, this will go up, that means Q by C will go up, and as a constant, as a consequence VDD will remain constant. That means, we find that the initially voltage drop across the resistor is maximum, where the voltage drop across is 0, then as the time passes voltage drop across the resistance will become 0, and voltage drop across the capacitor will become equal to VDD. Okay. So, this is how the charging occurs, but irrespective of this mechanism, we know that the energy transfer is equal to CL VDD square per I mean whenever it switches from 0 to 1, that we have seen, and the energy of CL VDD square by 2 will be lost in this resistor. Even if it is instead of a resistor, if we put a constant current, I mean if it is instead of a voltage, if we put a constant current source, even then that will take place. That will this will be linear and this will be also linear. However, that energy, so far as the energy dissipation is concerned, that will remain same. So, irrespective of the nature of voltage that is being applied or if it is charged through a constant current source, this will happen. So, this is the typical conventional charging. Now, let us consider a situation where we shall use a current, time varying current IT which is being applied across a resistor R, and you have got a capacitor C. Of course, we can put a switch in between, here we can put a switch. So, at time t is equal to 0, the charge across this capacitance and so on. So, in such a case, what we are trying to do, this current is no longer constant, and in such a case let us see what will be the equation for current. So, a time dependent current source I t is used to charge the capacitance C, and this circuit is used to model a CMOS circuit with certain output resistance driving a capacitive load. So, that means, we are trying to model a CMOS circuit, later on we shall see how it can be modeled. So, the load capacitance is not having any charge at time t 0 as I have told, and the voltage across the capacitance as a function of time V c t is given by V c t is equal to 1 by C into I t into t. So, this is the 1 by C into current into t, that is how the charge will take place. And what is I t? And I t, that is time varying current, will be equal to C into V c t by t. Let us assume this time varying current is arising because of this variable voltage, which is a time varying voltage that is being applied across it. So, if we substitute this here in this particular expression, we get V c t, we substitute not in this equation, but we shall try to find out the energy dissipation is equal to R into I square into dt. As you know, I square is the dissipation and over a time period t. So, let us assume 0 time taken to charge to a particular voltage level is time t. So, if we substitute this value here, then we get R into I square t into t is equal to R c by t into C, say C v, let us assume V d d square, let it not be, since it is a time varying constant, time varying voltage, let it be V square t. So, we find that in this particular expression we are observing that it is R c by t into C V d d square into t. Now, in what way it is different from our previous expression? Let us consider the case when t is greater than 2 R c. So, if we can substitute 2 R c here. So, if we substitute 2 R c greater than 2 R c here, then what will happen? When t is equal to 2 R c, then this value will become equal to half C V d d square. So, that means the V c t square V t square. So, that will be the voltage whenever that will be the energy dissipation when t is equal to R c. Now, if we can make t greater than 2 R c, then what will happen? Then obviously, this will be lesser than half C V d d square t. That means, this expression will become less than half C V square, because t is greater than 2 R c. So, since it is less than, sorry, it will be less than half C V square. So, this power dissipation, energy dissipation is less, let me write here, E dissipation will be less than half C V square whenever t is greater than 2 R c. Now, question naturally arises, how we can really make t larger than 2 R c? That is quite easy to do, because we are applying a voltage which is time varying. So, we can, instead of applying the voltage to rise quickly, we can apply another voltage which rises more slowly and like that. So, we can apply a voltage of this type, that means which rises very slowly, and as a consequence the time that t can be made, I mean we can make larger than 2 R c, that means this time can be made much larger than 2 R c. So, whenever we make t greater than 2 R c, then what is happening? We are able to reduce the energy loss per switching less than half C V d d square. Is there any other way to reduce it? Another alternative is, that first is time, second is there is another very important parameter. Earlier we have seen this resistance was not part of this expression. because the dissipated energy is proportional to R. This R was not present in our earlier expression. So, in this R was not present in our earlier expression. So, by making T larger than 2 R C, that is a one possibility of making it smaller than half C V D D square V C square. Another alternative is to reduce the value of R to make it smaller than half C V D D square. That means, the dissipated energy is proportional to R, a smaller R results in lower dissipation, unlike conventional case, because in conventional case, as we have seen, R does not figure out in this expression, because in this expression whether you are charging with a constant voltage or a constant current, irrespective of that, R is not present in this expression. But in this case, that in case of adiabatic charging, we call it adiabatic charging, when the voltage is slowly applied, time varying voltage is applied, which gradually rises from 0 to V C or V D D, then obviously an expression, in the expression R is appearing. So, this is how we can reduce the energy dissipation. This is the basic idea behind adiabatic charging. So, charge moves efficiently from power supply to load capacitance by using slow constant current charging. So, you may be asking, what is the basic physical phenomenon involved in it? Basic idea is very simple. You see, you have got a R and a C, and if we apply a constant voltage here, then what happens initially, as we have seen, there is a voltage of V D D which is present across this R. So, maximum current flows, and subsequently of course, it decreases as the voltage builds up here. Now, if we apply a voltage which is somewhat like this, and in that case what happens, if we can make this voltage here, say this is your V C and voltage here V O, this difference is very small, that means V C minus V O is equal to delta V, that is very small, then power dissipation across this will be delta V D square by R. That means, if we can make this difference voltage small, then very small power dissipation will take place. That is the basic idea. In fact, by making it by extending the time t, that is precisely we are doing, that voltage difference between this output of this capacitor and that is applied to the resistor, that is becoming smaller and smaller, and that is leading to smaller power dissipation in this resistance. So, that is the basic idea behind adiabatic charging. Now, reversing the current source will cause the energy to flow from the load capacitance back into the power supply. So, the power supply must be so designed to retrieve the energy fed back to it, that is to realize the reversible circuit. So, adiabatic switching circuits require non-constant, non-standard power supply with time varying voltage like this. So, it will charge from 0 to a voltage, let it be V D D in time t, and the supply is called pulsed power supplies, and we shall see how we can transfer back the energy to the power supply from the circuit. So, this is the adiabatic amplification circuit. Circuit consists of two transmission gates, as you can see, you have got one transmission gate here, another transmission gate here, and inputs and outputs are dual rail encoded to avoid use of inverters. If we do not use dual rail, then you have to use static CMOS inverters, and if you use static CMOS inverters, that will lead to that non adiabatic charging and discharging. So, to avoid that, in adiabatic logic circuits, you will always use dual role encoded circuits. That means, you will be realizing both Y and Y bar. So, you may consider it as an inverter or buffer. So, you see here you are applying a time varying voltage V A here. So, initially what is happening, depending on the input X, depending on this input that we applied here X, that is also applied across the switches, one of the path will become one of the output will become high and one of the output will become 0. So, for the output which becomes high, the capacitor at that point will charge through this to this transmission gate. On the other hand, when the output is 0, that discharge will take place not only through this I mean will primarily take place through these transistors. That means, when this is high, this output will be 0, and when x is bar is 0, then this will be high. So, this is how these two transmission gates can be used to realize adiabatic amplification. So, what we are doing here, depending on the valid input value, amplifier is energized by a slow voltage ramp. That means, we are applying this voltage and gradually charging it, and the corresponding point, one of the output will become high and one of the output will become low. Then these output values are used during this period, during this period it will be used. This will remain stable during this period. That means, it will feed the succeeding stage during this stable period. Then after this stable period is over, what will happen, this voltage will gradually ramp down, and in that case the charge, those are the which is stored in this node, will be transferred to the power source, back to the power source. That means, what is happening, you are transferring energy during this phase to the circuit, and during this phase you are transferring back the energy to the from the circuit to the power supply. So, that is how reversible operation is taking place, and you will require this kind of supply voltage. Okay. Now, how do you really realize adiabatic logic gates by using this type of circuits? So, we have a supply voltage VDD, and this is the traditional that traditional CMOS circuits. You may recall that we realize F bar that corresponds to the NMOS network, and here is the PMOS network that essentially is that this path is open when F is 1. So, this is the traditional CMOS circuit, where you apply a constant voltage VDD, and there is a load capacitance CLs. So, this is being modified to realize a adiabatic circuits. So, in this case we are applying the input here, and we have two outputs, F and F bar. This is F bar and this is F, and instead of using a fixed voltage here, we are applying a time varying voltage, that pulsed power supply that I mentioned earlier, that this pulsed power supply that is being applied to this input. So, to this input you are applying that means the circuit which is realizing F as well as the circuit which is realizing F bar. To both the circuits we are applying this pulse power supply, and we are applying the input to both of them. Then we are getting two outputs, obviously one will be out, another will be out bar, or F or F bar. So, let me illustrate this with the help of before that let me explain how exactly you can realize any gate by using this. Basic steps are like this: replace each of the PMOS and NMOS devices in the pull up and pull down networks by T gate transmission gates. So, whenever you are realizing these circuits, obviously you will not be using NMOS network which is used here, or PMOS network that is being used here. You will be replacing them by transmission gate. Then use expanded pull up network to drive the true output, and expanded pull down network to drive the complementary output. That means, we are driving these two networks with the help of transmission gate circuit, and both networks in the transformed circuit are used to charge and discharge the load capacitance, and replace VDD DC VDD by a pulsed power supply with varying voltage to allow adiabatic operations. So, these are the steps that you have to follow in converting a standard static CMOS gate to a corresponding adiabatic gate. And here, for example, the realization of a AND net is shown. So, you can see here this VA, which is that pulse power supply that is being applied, and this part this is a two transmission gate which is driving a capacitor, and which is realizing F. That means, whenever this is a AND gate, that means when both of them are 1, you see both of them are 1, that means this path will be closed, only then this will become, this output will become 1, and when both of them are 0 or any of them is 0, then when any of them is 0, then in case of NAND gate, so this will be the output of AND and this will be the output of NAND. That means, it will realize NAND opposite of AND. So, NAND means if any of the input is 0, then there is a path to this, because 0 means this transistor will be on or this transistor will be on. So, there will be a path. So, this will realize the AND NAND function, and you will apply a pulse power supply here. So, we can see by following this step that I mentioned, we have realized this AND NAND network. We have converted this circuit, I mean the static CMOS AND gate, NAND gate into a corresponding adiabatic CMOS NAND and NAND gate, because it will realize both AND and NAND, that because it is dual railed logic. But one point you must notice here, the number of transistor is doubled. So, here as you can see earlier, if you realize a 2 input NAND gate, you will realize 2n, that means 2 plus 2 4 transistors, but here the number of transistors is 1 2 3 4 5 6 7 8. So, number of transistor is doubled whenever you go for adiabatic CMOS logic circuit realization. Moreover, you have to put lot of effort in realizing this pulse power supply, and particularly realizing pulse power supply is a little difficult task, and it has to be designed in such a way that recovered node energies are stored in the adiabatic power supply, and two principal alternatives for energy storing circuit elements are capacitor and inductor. As you know, you have to use some energy storing device in the pulse supply, and typically in electronic circuits or electrical circuits, you can use either capacitor to hold charge, or you can use inductor. So, either inductor or capacitor can be used to for storing energy, and another alternative to use both. So, inductor and capacitor can form a LC resonant circuit, that means energy actually switches back and forth between L and C, and then that way you can realize the pulse power supply. So, it will act like a resonant circuit. So, energy will oscillate between the inductance and capacitance with a frequency proportional to the inverse of the square root of the LC product. That means, the F will be equal to 1 by root LC. So, that is the frequency of oscillation. So, you can generate a near sinusoidal waveform if energy is replenished regularly. So, but unfortunately, whenever you are going for VLSI realization of an inductor is very difficult, particularly the inductor realized by using VLSI circuit on a chip will have very low Q. The Q value is very low, and there are many limitations like lower Q, timing errors causing ringing or damaging voltage spikes, jitter for variable capacitance loss, and that is the reason why instead of using inductor, particularly capacitor based storage elements are normally used in realizing pulse power supply. We are not going into the details of realization of pulse power supply, that is a area of research, how we can realize pulse power supply very efficiently. The efficiency has to be very high, otherwise if the pulse supply is not efficient, whatever gain you achieve in adiabatic circuit will be lost in the power dissipation of the power supply. So, that is also a very important area of research, realizing pulse power supply in adiabatic circuits. Anyway, let us consider another alternative by which a capacitor can be charged adiabatically. So, here what is being done, a stepwise charging circuit used. What do you really mean by stepwise charging? So, instead of charging a capacitor, say you have got a capacitor, instead of charging it directly to a voltage VDD through, obviously it will be through some resistance. So, instead of applying a voltage VDD, then it will charge to VDD. this capacitor, and you know that power loss of CL VDD square will take place. Instead of doing that, what you can do, let us assume first we charge the capacitor to say VDD by 2, then how much energy will be lost in charging? Half CL into VDD by 2 square, that is your 1 by 8 CL VDD square. Now let us assume another supply you apply, where when you after this charging is over, now you charge it to VDD. After it has been charged to VDD by 2, now you apply this switch is closed after this charging has taken place, and this is now turned off. So, you have two switches here. First this switch is closed to charge it to VDD by 2, then this switch is closed to charge it from VDD by 2 VDD. And again in that case what will happen, there will be another in that case what will be the power loss? Again there will be a, since it is charging from VDD by 2 to VDD. So, a loss of CL 1 by 8 CL VDD square take place. That means, it will be, if you put them together, it will be 1 by 4 CL VDD square. So, we find that, and this can be represented as 1 by half into n CL VDD square, but if we generalize it, that we shall be charging by using n steps. So, where n is equal to 2 in 2 steps, then it is 1 by 4, and suppose you use n steps, and that is what is being shown in this diagram. We are using n steps in charging this capacitor. So, initially this capacitor is discharged with the by turning this transistor on. So, the voltage is 0. Now, first you this particular switch number 1 is closed, it will charge to a voltage V 1, then this switch will be turned off, switch V 2 will be closed, it will charge from V 1 to V 2. In this way, it will go up to voltage V n in n steps. That means, whenever you do the charging in n steps, then the total energy dissipation by using a stepwise charging is equal to n into each step, that is equal to n into CL VDD square by 2 n square, as we have already seen. So, this will be equal to CL VDD square by 2 n. So, what is happening here, whenever you do the charging in n steps, there is the energy loss for charging from 0 to VDD, or in this case V, let us assume, is 1 by n times smaller compared to if you do it in one step. So, if we make, say, suppose n is 8, that means the power dissipation will be 8 times smaller than the traditional energy dissipation that take place in one step charging. So, this will require multiple supply voltages. So, we have seen here these switches can be easily realized, but you have to apply, you have to realize multiple supply voltages. So, from a single supply voltage you can generate n supply voltages, and then n supply voltages are to be present here. Obviously, this will increase the cost of implementation. Not only that, you have to do the routing, that power rail routing for all these n supplies to the circuit. And as I mentioned, you can do the charging. The way you can do the charging, you can do the discharging as well. So, that means, you can also transfer back the energy back to the source by reverse operation, that is discharging the capacitor in the reverse order. So, whatever way you do, you will require n power supplies, and n power supplies have to be connected to the capacitor by using this circuit. So, this stepwise charging can be done, but number of power supply requirement is high. Another approach is to reduce the cost of implementation is to use capacitor tanks. You know what is being done, little larger capacitors are used to hold the value of different voltages. That means, what you will be doing, say suppose this is the voltage V n. Now, what we will do, you will selectively turn on these transistors to charge these tank capacitors to some voltages, to different voltages, like earlier we have seen voltage V1. So, you will charge this capacitor to voltage V1, then you will charge this voltage capacitor to V2 and so on. So, you will require n minus 1 tank capacitors, which will be tank capacitors are essentially capacitors of little large value. So, because so that they can supply energy for the operation of the circuit during its normal mode of operation. So, all supplies except one are replaced by tank capacitor, and conventional single supply voltage can be used. So, this is your conventional single supply voltage, and overhead limits the practical number of steps below 10. Obviously, this will also have overhead like the previous case, and whenever we use this approach for generating the those switched power supply, then the number of steps that can be used in practical circuits is limited to 10. It cannot be, because of large overhead we cannot really have large number of steps, but larger the number of steps the reduction in energy is more. However, because of practical limitations this is not being done. Okay. Now, as I have told, this implementation of fully adiabatic circuits are very expensive. You will require large number of transistors. It has been found that a fully reversible bit level pipeline 3-bit adder requires 20 times as many devices as a conventional one and 32 times the silicon area. So, you can see it has got very large overhead. So, this has motivated researchers to apply adiabatic technique to realize partially adiabatic logic circuits. So, instead of using fully adiabatic logic circuits, partially adiabatic logic circuits can be used to reduce the with some compromise, but still a significant reduction in power dissipation. How can it be done? So, you will see that most of the partially adiabatic circuits use cross coupled devices, that means flip flop like cross coupled devices connecting two nodes that form the true and complementary outputs. When a voltage ramp is applied, the outputs settle to one of the states based on the outputs. That means, in this case we do not really use transmission gates, rather than we use traditional NMOS and PMOS transistors. However, there is a non-adiabatic dissipation of approximately half CL VTH square for transition from one state to another. I shall explain that as I discuss a particular type of circuit. Let us consider, sorry. So, this is a partially adiabatic circuit style, one of the partially adiabatic logic style. Here, as you can see, we have got pulse power supply applied here, then two inverters which are connected back to back, and then these two inverters are connected back to back. Then we have these these PMOS NMOS transistors A, B, and here A bar, B bar NMOS transistor connected in parallel. Obviously, they are realizing the complementary functions which are connected in parallel with these NMOS transistors of those inverters. So, both inputs and outputs are dual encoded, and V phi is connected to the pulse power supply, this one, and initially there is a non adiabatic dissipation of approximately half CL VTH square. What is the reason for that? You will see that depending on the inputs A and B, one of the output will be 0. When this input is 0, then this voltage will be 0. 0 means this transistor will be on, provided the voltage here is greater than this by a voltage of VTH. Otherwise, this transistor will not turn on. So, this will be minus VTH, this voltage has to be minus VTH with respect to this. So, as you know, this pulse power supply is charging from 0, and that means initially this V phi is 0 at time t is equal to 0, and up to this time, say some time t 1, this voltage is not reaching VTH P. That means, the VTH P, the threshold voltage of the PMOS transistor. Then what will happen? That means, this transistor is not turned on. That means, no adiabatic charging is taking place of this node for this part of the circuit. So, that means this particular part of charging is taking place non adiabatically, and as a consequence there is a energy dissipation of half CL VTH square. Subsequent part of course will be adiabatic charging, that means the output voltage will follow the this voltage. So, but initial part will not follow, it will be as if suddenly after some time a voltage of VTH is applied here, then it will charge to 0 to VTH the initial part. So, this kind of this happens, and this non adiabatic dissipation takes place in this particular circuit. Now, there are several that adiabatic logic circuit families. I shall briefly mention about them. One is partially adiabatic circuit style, that is your that is actually this is one of the partially adiabatic circuit style known as ECRL, energy charge recovery logic. Here you can see two PMOS transistors are connected back to back. In most of the in all of the partially adiabatic circuits, actually this type of cross coupling is used. Now, here you have got two networks of NMOS transistors, one is realizing F, another is realizing F bar. So, the network of NMOS transistors constitute the evaluation network. So, this is how you are realizing this the energy charge recovery logic. And here also depending on the inputs, obviously one of these this node will be, I mean there will be a discharge path through one of these nodes, NMOS transistors will turn on, and one of them will not be having any discharge path. That means, if this output is I mean there is a discharge path, this will be 0, this will turn on this transistor and that will charge this output to 1. So, this is how one of them will be charged to 1 and one of them will become 0 depending on the input combination that you applied here and the circuit that is being realized. And there is another logic family, logic circuit, which is part of that partially adiabatic logic circuit family, which is known as 2N 2N 2P inverter, 2N 2N 2P logic style. Here as you can see we have inverters, then we are having these NMOS transistors connected in parallel with these NMOS transistors of these inverters. So, this is same as what I have explained earlier, it is and how the NAND gate is realized by using this. This is essentially this 2N 2N 2P implementation of circuit. So, this is the inverter that is being realized. And the primary advantage of this 2N 2N 2P over ECRL is that the cross coupled NMOSFET switches result in non floating outputs for large part of the recovery phase. That means, when the recovery is taking place, these outputs remain floating for certain duration in this particular case, and as a consequence that adiabatic transfer does not take place for that part, and as a non adiabatic loss takes place. So, that does not happen in this 2N 2N 2P circuits, and that is the advantage of this logic style over ECRL logic circuits. Coming to the third type, which is one of the most popular, that is actually known as positive feedback adiabatic logic circuits, PFOL. Here actually instead of connecting the NMOS transistor network in parallel with this NMOS transistors, they are connected in parallel with the PMOS transistor. So, you can see here the PMOS transistors are I mean this PMOS NMOS networks are connected in parallel with the PMOS network. So, the input NMOS network is connected in parallel to the PMOS transistors. So, in a PFOL gate no output is floating and all outputs have full logic swing. So, that means, here also just like that this 2N 2N 2P circuit, here also we get full swing at these outputs, and there is the outputs do not remain in floating condition. So, for major part of the circuit, and as a consequence this is also advantageous, and lot of simulation works have been carried out. I shall discuss about them and I shall give their results. So, PFOL shows the best performance in terms of energy consumption, useful frequency range and robustness against technology variations. So, this has been established by simulation that out of the three members of the non-adiabatic, partially adiabatic logic circuits that I have discussed, this p-fall has been found to work better. And actually the circuit operates in 4 phases, as you can see. During this phase, during this part, evaluation take place. Evaluation take place means and in this part inputs are stable, and output is charging from 0 to some level, say VDD, and during this evaluation is taking place, and accordingly these nodes, these output nodes will charge to some certain values, because depending on this input combination, one of them will be output will be 0 and one of them will be 1. So, this is the evaluation, and after this evaluation phase, these outputs will have some output values depending on the input combinations, and during this hold phase, this output will be applied to the succeeding stage, and after that is being used by the next stage during the hold phase, that energy is recovered in the third phase, recover phase, and the energy that were stored in these node capacitors now are transferred back to the pulsed power supply during this recover phase, and then of course, it is the wait phase before another evaluation starts. So, this is how the p-fall circuit works in 4 phases, and you can implement pipelined p-fall circuits using this approach. Yeah, for example, here how the 4 phases work, and that is being shown here. This is realizing a sum cell. So, you can see this is the sum cells NMOS transistor network. One is your sum ABC, that means it is essentially realizing 3 inputs, sum ABC, and it is sum bar complement of sum ABC that is being realized here. So, the arrow shows when the data is transferred from one gate to the consecutive gates. As I mentioned, during this part it is getting transferred to the next stage, and similarly in this part it is getting transferred to the next stage. So, by using this kind of 4 phase circuit, you can realize pipelined implementation of p-fall logic circuits. So, 4 phases will be driving the 4 pipeline stages. Okay. Coming to the comparison of energy, you can see here the top line corresponds to the static CMOS, and compared to that it is being compared with ECRL, 2N, 2N TP and p-fall. Obviously, p-fall is giving the maximum reduction in or dissipation of energy. So, energy consumption per switching operation versus frequency of CMOS circuits. That means, as I have mentioned, the energy consumption will be more when the clock frequency is smaller. However, there is this part of the energy consumption is occurring because of leakage power. Leakage power, when the frequency operation is low, then leakage power is more, because that in this part during this part lot of leakage power will take place, and that is the reason why this part leakage power dissipation will take place. Then of course, the energy power dissipation will remain more or less constant, and then it will keep on increasing as the frequency is increasing. So, here actually this diagram shows how exactly this occurs. For example, adiabatic loss, as we know, increases as the frequency of operation increases, because it is proportional to frequency. Smaller the operation, larger is the saving, and leakage loss, as you can see, smaller the frequency of operation, leakage loss is larger. So, you can see this is the total power dissipation if you take into account the dynamic and static power. So, there is a group working in this area from the Technical University of Munich. So, they are carrying out lot of research work on adiabatic logic circuits, the impact of process parameter variation on energy dissipation in adiabatic circuits. So, they are doing all these works, and here is another simulation result, how it shows that how this top layer corresponds to the static CMOS, and how the for adiabatic p-fall circuits, it is a p-fall inverter with load capacitance of 10 picofarad and realized using 0.13 micron technology. You can see how the energy dissipation occurs and how it varies with the frequency and also with the width of the PMOS transistor. So, the variation of the width of the PMOS transistor and also along for the variation of frequency, how it occurs, that is being shown in this result. So, we can conclude our lecture with few statements. So, adiabatic circuits trade dynamic power for delay, as you have seen, and adiabatic circuits are slow by today's standards. As you have seen, they can operate only in the megahertz range, not in the gigahertz range. They are much slower in today's standards, but there are many applications where we can use these adiabatic circuits. For example, pacemaker, which need not really operate at a very high frequency. No speed of operation need not be very high, but saving of energy is extremely important, because you cannot replace the battery because every day, and battery replacement is hazardous. So, in such cases obviously it can be used. Then it requires 50% more area than static CMOS, as you have seen, and design is much more complicated, but a lot of research work is going on to get efficient design. And particularly whenever you want to use adiabatic circuits, you have to identify applications where adiabatic techniques outperform conventional ones. So, in such cases we can use adiabatic circuits. So, with these concluding remarks, we have come to the end of today's lecture on adiabatic logic circuits. Thank you.